Welcome to the lesson on real numbers. At the end of this lesson, you will be able to define real numbers and explain their decimal expansion. You will also be able to express the decimal expansion of a rational number in the form of p divided by q and determine an irrational number between two rational numbers. You will also be able to visualize the representation of real numbers on the number line. We know that a rational number is a number that can be expressed as a ratio of two integers, p and q, where q is not equal to 0. A collection of rational numbers is represented by the capital letter Q. 15 divided by 8, 2 divided by 3, and 11 divided by 7 are some examples of rational numbers. But there are some numbers which cannot be expressed in the form of p divided by q, where p and q are integers and q is not equal to 0. These numbers are called irrational numbers. Here are a few examples of irrational numbers. You note that the square root of any prime number is irrational. There are infinitely many rational and irrational numbers. The collection of all rational numbers and irrational numbers together is called the collection of real numbers. It is represented by the capital letter R. A real number is either rational or irrational. Here are examples of real numbers. Let's review the examples of real numbers. Consider the rational numbers among the real numbers. Solve each of them as shown. The following are the remainders and the divisors in each case. Let's observe the divisions carefully. Here are the conclusions based on the observations. The remainders become 0 after a certain stage or repeat themselves. If the remainders repeat, then the digits in the quotient are also repeated. Here, two cases arise. On solving 15 divided by 8, the remainder becomes 0 after some steps, and its decimal expansion is equal to 1.875, since the decimal expansion of the rational number is the quotient of division. In this case, the decimal expansion terminates after certain steps. The decimal expansion of such numbers is called terminating. In the second and third case, the remainder never becomes 0. In these divisions, the remainders repeat after a definite stage. Here, these blocks of digits repeat in the quotient of the divisions. We say that these expansions are non-terminating recurring. Commonly, we represent the recurring digits in the quotient with a bar on top of it. We read this as 0.6 bar. All rational numbers can be expressed either as terminating decimal expansion or non-terminating recurring decimal expansion. Let's now express a terminating or non-terminating recurring decimal in the form of p divided by q, where p and q are integers and q is not equal to 0. Let's begin with the first example. Here the decimal expansion is terminating. Converting a terminating decimal into a fraction is very simple. Multiply and divide the decimal by 1000 since there are 3 digits after the decimal point. The obtained fraction is a rational number. Now, we'll consider the non-terminating recurring decimal 0.6 bar. Consider a rational number x. The decimal expansion of x is 0.6 bar. This can also be expressed as 0.666 and so on. Here only one digit 6 is repeating itself. So we multiply the equation with 10. The right-hand side of this equation can be expressed as the sum of an integer and a decimal. The right-hand side of this equation is now equal to 6 plus x. Let's solve this equation. We get x equal to 2 divided by 3, which is a rational number. Similarly, every non-terminating recurring decimal expansion can be expressed in the basic form of a rational number. On summarizing, we can say the decimal expansion of every rational number is either terminating or non-terminating recurring. On the other hand, the decimal expansion of an irrational number is non-terminating, non-recurring. Here is an example of an irrational number. Some more examples of irrational numbers are the square root of 2 and pi. There are infinitely many rational and irrational numbers. Can you find an irrational number between two rational numbers? Let's try. Consider two rational numbers, 1 divided by 3 and 2 divided by 3. First, we'll find the decimal expansion of the first rational number. Thus, 1 divided by 3 is equal to 0.333 and so on. Next, let's find the decimal expansion of the second rational number, 2 divided by 3. 2 divided by 3 is equal to 0.666 and so on. Can you find a number which is non-terminating, non-recurring between the two decimal expansions? We can find a number of this pattern. Here, we have put increasing number of zeros between two consecutive 34s. This number is non-terminating and non-recurring. Similarly, we can find many such numbers. We have seen that a real number can be expressed as its decimal expansion. You're already aware of representing rational and irrational numbers on the number line. The decimal expansion of a real number helps us to represent it on the number line. Let's represent 0.6 bar on the number line. Here, this decimal expansion is non-terminating recurring, where the digit 6 is repeating itself. We know that this decimal lies between 0 and 1. Let's look at the section closely by using a magnifying glass. We divide the section into 10 equal parts. Now, we'll represent each part as shown. On observation, you can notice that this decimal expansion lies between 0.6 and 0.7. Let's again look at the section closely. We again divide the section into 10 equal parts and represent them as shown here. Now, you might locate this decimal expansion between 0.66 and 0.67. Again, focus this section on the number line. Let's divide the section into 10 equal parts again. Represent these parts as shown. Now the decimal expansion lies in this section of the number line. Let's magnify the section and observe closely. Next, divide them into 10 equal parts and represent them as shown. Now, you can locate the decimal expression in this section of the number line. If we keep on continuing this process, then the degree of accuracy will be more. This process of visualization of representing a decimal expansion on the number line is known as the process of successive magnification. Similarly, we can also visualize a non-terminating, non-recurring decimal expansion on the number line. Based on this visualization, we can conclude that every real number can be represented on a number line uniquely. Let's recap. The collection of real numbers is the collection of all rational numbers and irrational numbers together. It is represented by the capital letter R. A real number is either rational or irrational. A rational number can be expressed as its decimal expansion. In case of division, if remainder becomes 0 after a certain stage, then the decimal expansion is terminating. If the remainder never becomes 0 but repeats after a certain stage, then the decimal expansion is non-terminating recurring. The decimal expansion of a rational number is either terminating or non-terminating recurring. The decimal expansion of an irrational number is non-terminating non-recurring. There are infinitely many irrational numbers between two rational numbers. Every real number can be represented on a number line uniquely.